Hello again. This is Math 1120 coming to you from the College of DuPage, and the title of this lecture is More About Discrete Probability Distributions. As always, please be an active learner as you watch this video. Let's start with the definition. A random variable is a numerical measure of the outcome of a probability experiment. So that means in any experiment, it will take on a value. So it is a function, but its value will be determined by chance. So it's a function whose value is determined by chance. Random variables are typically denoted using capital letters such as X. So in our coin flipping example, if the random variable capital X represents the number of heads in two flips of a coin, the possible values it can take on are 0, 1, or 2. Now the practice is that when you're talking about a random variable, use a capital letter like X, and when you're talking about the values of the random variable or the sample space, you use lowercase x. As another example, consider an experiment which measures the time between the arrival of cars at a drive-through. The random variable capital T describes the time between arrivals, so the sample space of the experiment is T is greater than 0. Now there are two types of variables, discrete and continuous. We have talked about continuous distributions before. A normal distribution is one of those examples, but discrete is a different kind. Let's talk about the differences again. So a discrete random variable either has a finite or countable number of values. The values of a discrete random variable can be plotted on a number line with space in between. So here's an example. A continuous random variable has infinitely many values, and the values of the continuous random variable can be plotted on a line in an uninterrupted fashion, like this. In other words, discrete random variables typically result from counting, and continuous random variables result usually from measurement. So let's do an example distinguishing between the two. Suppose the random variable x represents the number of A's that happens in a class with 15 students. Well, the number of A's would be these things, these values. These are the only number of A's that you could have. You couldn't have 3.5 A's. And so that means that this is discrete. Likewise, the number of cars that travel through a McDonald's drive-through in the next hour is a discrete random variable because its values come from counting. And the speed of the next car that passes a state trooper is a continuous random variable because it is measured. If the random variable s represents speed, then possible value of s are all positive real numbers greater than or equal to 0. Now, even though a radar may report that the speed of car is 37 miles per hour, it's actually, they're saying, oh, that's the closest number. So that's rounded off. That's in between these two, so it actually is an interval. So the probability distribution of a discrete random variable provides the possible values of the random variable and their corresponding probabilities or likelihoods. A probability distribution can be given in the form of a table, a graph, or even a mathematical formula. Here is an example of a probability distribution. So it's a table. Here are the outcomes, x, and here are the probabilities. They happen, p of x. Okay, so let's look at the example that we have. So suppose we ask a basketball player to shoot 3 free throws. Let x be the random variable, and it represents the number of shots made. So the values it can take on are 0, 1, 2, or 3, and we see this over here, and we've assigned probabilities. And so the probability of 3 means 0.51 means the probability that the random variable equals 3. That is, he hits 3 shots. 3 out of 3 is 0.51. Now, this is review, but we've talked about probabilities before, and certainly discrete probability distributions must follow the rules for probability distributions. So they must add up to 1. And the numbers themselves, the probabilities are going to be between 0 and 1, no negative. So the first rule states that the sum must equal 1, and the second rule states that each probability must be between 0 and 1 inclusive. And so if we look at this from the first earlier example about the person shooting free throws, you can see that all these probabilities are greater than or equal to 0 and less than or equal to 1, and they add up to 1. If you were to add them up, you could use Excel to test if it adds up to 1. Okay, so here's a problem that we could do. So which of the following is a discrete probability distribution? Well, this one is not, because you have a negative entry. They all must be bigger than or equal to 0. This one is not, because if you add up all these numbers, you get 1.18. It has to add up to 1 to be a probability distribution. This one is a probability distribution because all the entries are bigger than or equal to 0, and if you were to add those up, you do get 1. We again can graph probability distributions, and we're doing the same table here. So that means at 0 we're going to be 0.1. At 1 we're going to be plotting 0.10. At 2 we're going to be plotting 0.38, and at 3 we're going to be plotting 0.51. Now, graphs of discrete probability distributions help determine the shape of the distribution. So here you can see the shape is like this, and we could also talk about whether it's skewed left, skewed right, or symmetric. This is skewed left because you see the tail is going out in the left direction. Now, certainly when we have a probability distribution, we can talk about the mean and the standard deviation. So first we're going to talk about the mean. So here we have a table where we show 2, 3, 4, 5, and 6, and these are the probabilities that those various entries happen. Now, I could find a common denominator and write 0.2 as 2 over 10. This is 1 over 10. And so I actually could look at this as adding up the values. See, there's 2 2s, and there's 1 3, and there's 3 of these 4s. You see I'm getting that from there too. So I'm doing this, expanding this as a frequency, and I'm dividing by 10, and I do this. But notice what I get whenever I do that is I end up taking the value 2 times the probability. So it's 2 times 0.2. It is 3 times 0.1. It is 4 times 0.3. It is 5 times 0.2. And it is 6 times 0.2. And so now what that means is that the way I can find the mean is just by taking the value times the probability. So in other words, the mean of a discrete random variable, you multiply each value by its probability and add these up. You can see how that would be easy to do in Excel, and here's the formula. The mean of a discrete random variable is given by the formula mu sub x, and this is a population, by the way, is equal to the summation. You take x times p of x and add them up. That's what these symbols mean, where x is the value of the random variable and p of x is the probability of observing the value x. So let's do a problem. So here is a problem, and actually we've encountered this before. This is the guy shooting the free throws, but let's find the mean. So mu of x is equal to the sum. We take x times p of x. So it's 0 times 0.1. It is 1 times 0.1. It is 2 times 0.38, and it's 3 times 0.51. I add it up and I get 2.39, and that's approximately equal to 4. Now, do not, this is strong advice to you, so this is guidance for the entire course, I think. Do not round off until the end of the problem, and then the practice is, and this is what Sullivan says in his book, so if you're checking the answers that he has, this will help you do that. We will follow the practice of rounding the mean and the standard deviation to one more decimal place than the values of the random variable. That's just making it so you can understand that. So here the values it takes on are the units 0, 1, 2, 3, but we round to the 10th, but we wait till the end of the problem to round anything off. Okay, so how do you interpret the mean? Well, it can be thought of as the mean outcome of a probability experiment if we repeated the experiment an infinite number of times. So you remember we talked about x bar, meaning you would add up all the values that you get through n tries and divide by n. But the law of large numbers said that as n goes to infinity, this goes to the mean. So in other words, recall from chapter 5 that the independent means that the result of one trial do converge to the mean in the long run, and that's the law of large numbers. Okay, so let's then consider the basketball player, and let's talk about the mean free throws made. Well, one way we could do it is do what we get, and we get 2.13. We also, and this was in the last video, we could simulate this using these probabilities. So here I did actually a little simulation. So our first experiment, we get these numbers. Our next experiment, we get these numbers, and so on and so forth. And so what you end up with is x bar from all those. There's 100 possibilities in our little experiment. So x bar is going to be, you add them up, it's 235. And when you divide that by 100, you get 2.35. And that's very close to the theoretical mean, the long-term mean of 2.4. And as the number of repetitions of the experiment increase, we would expect x to get even closer to 2.4. The mean can also be interpreted as expected value. In other words, the expected value of a discrete random variable is the mean. That's another way to call it. And it's what you might expect to get. So let's do an example. A life insurance policy will pay a beneficiary a certain sum of money if they die. And here's the probability distribution, and this is based on statistics that they have from actuarial tables. So if the person survives, they will pay $350 for the policy, and the probability that they survive is this. And this is talking from the vantage point of the insurance company. So you see they get $350 if the person survives, and they don't have to pay anything out. And there's a good chance that they get to keep all that, so this is a good business. But the person was paying $350 for a $250,000 policy. And so what happens is, if he were to die, then the insurance company, and they would already have this, but they would pay out $250,000, so they would, but they already got the 350. So the net would be minus 249,650. So they'd be paying that out. That would be negative. And here's the probability that that happens, which is 1 minus the probability that the top one happens. So the expected value then is going to be the summation of p times p of x. So it's 350 times this number that's very close to 1. It's this negative number times this. You do the arithmetic, and it's 84.25. You see, the insurance company would expect to make 84.25 on every young man who buys this policy. And just to interpret it again, so the company expects to make $84.25 for each 18-year-old client. This says the profit is a long-term result. It does not mean it makes this much on each one, because unfortunately some of them die. It ensures, but rather than the average profit insured, this will be the average profit. Because it's a long-term result, the insurance idea will not work with a small number necessarily. But as you can see, with a large number, it's a great business. We can also talk about the standard deviation of a discrete random variable, and it's not going to surprise you when you think about it. Think about the analysis we did with the mean. If you take x minus mu of x whole squared times p of x, that's what you expect to be, and that's the square root of this. Now, it turns out that there's a formula that my engineering students get very excited about, because this is an easier formula to calculate. So it could be this definition, or it could be this one. and they're both equivalent algebraically. The square root of the summation of x squared minus p of x minus mu of x whole squared. Now realize that you take the, so what you do is you take mu of x is being subtracted from this sum here. And we'll do some calculators later, where x is the value of the random variable, mu of x is the mean, and p of x is the probability of observing a value. So either of these equations will work. In other words, the standard deviation of a discrete random variable is the square root of the weighted average of the squared deviations from which for which the weights are the probabilities, and the squared deviations from the mean. And so here is this one that we've studied several times. This is a person shooting free throws, but here's the calculation using the old formula and the other formula, and you see both cases we get over here we get the standard deviation is 0.4979, and over here that's what we get for the summation. Then I have to take the square root of that, so I get 0.7 after I take the square root. Here's the formula that I'm using. If I do the other calculation here, you see I get exactly the same thing. And note that again, the variance of a discrete random variable is the value under the square root, so it's the square of the standard deviation. And so here it's going to be this number that is 0.4979. So the standard deviation of a discrete random variable in the life insurance scenario, where this was our table, is 8,000. It's over $8,000. Now the reason this is large is because there's a large range. Remember what the standard deviation shows us of possible outcomes. Either you gain this or you lose $250,000. Now, when we're finding these standard deviations using Excel, there's a step-by-step process, but this is exactly what you would think it is. We're just really implementing the calculation, and we'll look at examples of this in the VCM and also in a moment. And in fact, we'll look at that right now. So we're going to look at a problem. Here's a problem. It's this about people waiting in line at Wendy's. So a Wendy's manager did a study, and he found that the number of people waiting in line would be something from 0 to 12, and this is the probabilities that we had. So we want to verify this is a probability distribution, draw a graph, compute the mean and standard deviation, and answer the question: what is the probability that exactly 8 people are waiting for lunch, and what's the probability that 10 or more, and is this one unusual? You know what to do. Let's see how you did. Well, first of all, this is a probability distribution, because if I add up the probabilities here, I get 1, and all of them are greater than 0. So this is a probability distribution. If I graph these, and I'm using Excel to graph them like we talked about, you get a picture that looks like this. They didn't ask, but this one is skewed to the right. I can tell from the picture. C asked for the mean, so getting the mean, I take these numbers and these numbers, I multiply them together to get this column, and then I add them up, and that is the mean. So that is 4.87. To find the standard deviation, I'm going to use this formula here. So I square each of my x values in this column, I multiply them by this, and I add all this up to get this. Now I'm going to subtract off the mean squared. So here is the mean, and if I square it, I get this number. And so when I subtract the two, I get this number, and I take the square root of that, and that's my standard deviation. They ask what's the probability of exactly 8. I just look on the table, and it's 0.63. What's the probability of 10 or more? These are disjoint sets, so I just either if 10 happens, 11 happens, or 12 happens, only one of them happens and they don't overlap. So these are disjoint events, so I can just add those probabilities together. And that's what I did, and I got 0.29. And yes, that is unusual because this is less than 5%. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself and of each other. May God bless y'all.